Lithium hydroxide is a core material in the battery industry, and its demand is explosively increasing. Particularly, the demand for electric or hybrid vehicles is going up worldwide due to the carbon neutrality policy. The lithium hydroxide is a key material for the high-performance electric vehicle batteries. As the countries around the world have encouraged the widespread adoption of electric or hybrid vehicles through policy measures, the demand for automotive batteries is expected to be increasing. Consequently, lithium hydroxide is undeniably an emerging key material for the future of the industry. Up to now, the global production method of lithium hydroxide has been using lithium carbonate as a raw material and utilizing calcium hydroxide or sodium hydroxide for production. However, it is widely known in the industry that this technology has many inherent problems. Firstly, the lithium hydroxide manufacturing technology using calcium hydroxide requires several stages of CCD process to concentrate low solubility products. As a result, the capital expenditure cost is significantly higher compared with other technologies, due to the excessive equipment costs and the need for large factory sites. Furthermore, since it can only be concentrated up to 30 grams per liter, far more below level of the saturated solution of lithium hydroxide at 130 grams per liter. A significant amount of energy is required for the evaporating concentration process, resulting in excessive operating costs. Another conventional technology is the one that uses sodium hydroxide to produce lithium hydroxide. A major drawback of the aforementioned technology is the significant byproduct of the hazardous waste, namely sodium sulfate. In advanced countries, such as Australia and Europe, sodium sulfate is classified as hazardous waste, making it difficult to dispose them. Furthermore, this technology incurs excessive additional costs in the cooling and evaporation concentration processes. The production cost of lithium hydroxide through this technology amounts to over $3,000 per ton. Addressing the shortcomings of existing technologies, the research laboratory led by Professor Myung-Joon Kim in Cheonnam National University has developed a new lithium hydroxide manufacturing technology. This technology completely eliminates waste generation and significantly enhances economic viability by recycling byproducts through reductive processes. The key advantage of this technology is its ability to recycle byproducts through reductive processes, completely eliminating waste generation. Additionally, the process costs are significantly lower compared to other technologies. Despite the generation of sodium sulfate, a hazardous waste that amounts to approximately 3 times the production volume of lithium hydroxide, Professor Kim's new technology allows for manufacturing of lithium hydroxide without any waste generation, thus enabling free from environmental regulations. Furthermore, this process concentrates the lithium hydroxide solution to saturation during the process. As a result, it significantly cuts down the energy costs associated with evaporation concentration of the final product compared to the conventional processes. Now, let's explore the lithium hydroxide manufacturing process developed by Professor Myung-Joon Kim's research team in Cheonnam National University. This process can be broadly divided into 5 stages. First, the raw materials, lithium carbonate and barium oxide, are dissolved to produce a lithium hydroxide solution. The precipitated barium carbonate is recovered through filtration. The recovered barium carbonate is reduced to barium oxide through a calcination process and reused in the preceding stages of the process. The high-concentration lithium hydroxide solution is precipitated into lithium hydroxide monohydrate through an evaporation concentration process. The precipitated product is dried to recover the final product, high-purity lithium hydroxide monohydrate. The described technology generates no waste at all. It utilizes both dry and wet processes, resulting in significantly lower operating costs compared to other conventional technologies. Now, let's delve into the details of the technology. First, the lithium carbonate and barium oxide undergo a stirring process to ensure homogeneous mixing. In the next step, the reactor is used to react the low-purity lithium carbonate and barium oxide to produce a lithium hydroxide solution. In this process, the generated solid product is moved to the next step for leaching using counter-current leaching technology, while the lithium hydroxide solution is concentrated to the saturation level. The precipitated barium carbonate from the leaching reaction is recovered as a solid one using a filter press. The dried barium carbonate recovered is mixed with a certain proportion of carbon. The mixture of barium carbonate and carbon is moved to a reduction calcination process using a rotary kiln, converting it into barium oxide, which is then reintroduced into the preceding reaction process. The highly concentrated lithium hydroxide solution is precipitated into solid lithium hydroxide monohydrate through an evaporation concentration process for recovery. Finally, through drying after evaporation concentration, removing any moisture from the product. Finally, we have a very valuable resource, high-value lithium hydroxide monohydrate, without generating pollutant. According to the United States Geological Survey, 87% of the world's lithium is stored in brine. Lithium within brine is extracted in the form of lithium carbonate, which serves as the raw material for this technology. The lithium production from brines increases annually due to technological advancements, and Professor Kim's technology is optimal for converting lithium carbonate produced from brines into lithium hydroxide. This technology does not generate waste, making it environmentally friendly. It also reuses byproducts through reduction heat treatment during the process. As a result, it is an economically excellent technology that can save on raw material costs. Furthermore, the cost incurred in the byproduct reusing process is only for the consumption of such reducing agent as carbon and energy, resulting in the production of lithium hydroxide with a purity of over 99.9% at approximately 30% lower cost per ton compared to the conventional technologies. The research laboratory led by Professor Myung-Joon Kim in Chonnam National University will continue to lead the development of cutting-edge technologies for resource processing and recycling as one of the representative National University experimental laboratory. Thank you for watching with interest.